All right, what up? All right, let's do this last lecture. For task 8, that's what we want to get you to today. For this one, we're going to use movie data with cast lists. That's going to come back. All that setup we did with movies, it's going to pay off here. We're going to use just the cast list, not the ratings this time. So we don't have to add any ratings to these movies. But what this class does, what this test is doing, we're going to create this degrees of separation class with a constructor that takes an array list of movies that, as I just said, importantly has cast lists, but you don't have to add any ratings to these if you don't want to. And you do have an option, whatever your preference is, to load these movies up. You can create your test files and call the read movies method, or you can create these array lists manually. So we've just had 2 tasks, 6 and 7, where we messed with files a whole bunch. We did lots of file stuff. If you're sick of file stuff by now, I already put you through it. You already got plenty of practice with files and testing with test files. If you don't want to do that for this one, that's fine. So whatever preference you have, either creating your test files and calling read movies, or manually creating your array lists like we did back when we first started working with movies. Either way is fine, but you need to give this thing an array list of movies. And then we have just one method. I like these types of assignments where the description of what you have to do is pretty succinct, pretty straightforward, but then actually completing the task is, has some nice complexities, a little bit of difficulty, to be able to give you a challenge and let you learn a whole bunch. But you're not getting bogged down on create 3 classes with all these methods and everything. What you're asked to do is much more straightforward and doesn't take too much of your brain power. It's accomplishing the task that you're asked to do that's more of the difficulty. So that task is the degrees of separation method. So for this, you're going to get 2 strings representing cast members or actors in these movies in the data that you're given. Possibly they might not be in any of the movies, which is one of your edge cases. But given two actors, you're computing the degrees of separation between those 2 actors, which is the number of movies you would have to traverse to get from one actor to another. So for example, if 2 actors were in a movie together, we say their degrees of separation is 1. You traverse just one movie, the movie they starred in together. And if you can go through multiple movies, so if actor A starred in a movie with actor B, who starred in a movie with actor C, but A and B never starred in a movie together, then A and B's degrees of separation would be 2, because you have to traverse 2 movies to get from one to the other. So that's our definition of degrees of separation. You can check out the Wikipedia article linked here if you want a better explanation of what exactly that means. We're going to see throughout today's lecture that that's going to relate directly to distance in a graph, and I'll walk you through today's lecture. Today's lecture is pretty much getting you to the point of computing this degrees of separation, which is distance in a graph. Is what it's going to boil down to. We're going to create graphs and compute distance in the graph. So degrees of separation, the definition is meticulously structured, I guess. That's not true. I just used the definition of degrees of separation. But it's chosen because it directly correlates to what we're going to be able to do with graphs and breadth first search, computing distance between 2 nodes in a graph. That's what it's going to end up boiling down to. Before that, we have a few edge cases. The distance of an actor to themselves is 0. So if you're given the same actor twice, their distance is 0. If 2 actors, if there's no path between 2 actors, if there's no way to get from one to the other, if they've never, there's no path of movies to get from one to the other, we're going to return -1. Their degrees of separation is infinity, but we're going to return -1 to indicate that, because we're returning an int, and there's no way to represent infinity in an int. For example, if we had doubles, we could return positive infinity as a double. Can't do that with an int, so we're going to return -1 to indicate that there is no connection between those 2 actors. So with that, that's what you're asked to do. That's task 8. With that, the testing utility method, there is none. Task 8 and Task 1, the only two without testing utility methods. The reason for that is the method that we're testing returns an int. What am I going to have you do for a testing utility method? Testing utility method would be given two ints, check if they're the same. I mean, I guess I could have you do that, but I see that as completely pointless. There's no reason to do that. You can just do assert equals two ints, and it does the same thing. So no reason to have any testing utility method, so I'm not going to make one up just to make you go through something. We're just going to skip it. And then the testing utility, again, you can either create your test files or create your array list manually. But once you have your set of movies with all your actors in those movies, manually compute the degrees of separation and use those as your test cases for your pairs of actors. For this one of the big things that you're going to have for your testing, you're going to have at least one test case that's a bit tricky. And this is always the case. I don't think I've harped on it very much this semester, but this is always the case that your test cases should be trying to trick your code. Maybe trick's the wrong word, but should be trying to challenge your code. There's a temptation when writing test cases to just write some really softball test cases that any code, no matter how crappy it is, can just knock these test cases out of the park and just absolutely crush these really easy test cases. So, and then when you submit to Autolab says, hey, you didn't test all these features because your tests are just really weak testing. Because it's very easy for an incorrect solution, something coded very poorly, that gets like the easy test cases, but is wrong on most test cases. It's very easy for those to pass your tests if you have just a couple, like a handful of really weak tests, really easy tests. Like in this example, like two movies where there's only like 3 different actors and your distance is supposed to be 2. For this one specifically, make sure you have at least one test case where there are multiple paths of different length between 2 actors. So you want to challenge the code. The code should get a challenging test case where maybe there is a path of length 2, so the degrees of separation is 2, but there's also several ways that you could get from the one actor to the other with length 3, and your code has to be smart enough to be able to find that path of length 2 instead of getting trapped in one of these paths of length 3. That is definitely one of the things that I'm expecting you to test, that Autolab's checking to make sure that you're testing, giving at least one fairly challenging test case. But I don't go overboard on that. It's that one, at least one test case that has multiple paths of different lengths. Preferably the length should be just differing by 1 also. Not to give it away, but that's it. And then I'm not really hammering you on the testing requirements anymore. At this point in the semester, I'm pretty well backed off, except for that one case that I just explained. I'm pretty well backed off on the testing requirements. Because at this point in your career, you need to be able to test on your own without anything saying, hey, you need more tests, hey, you need more tests, hey, you need more tests. Nobody should have to tell you that anymore. You should know by going through 116, going through all these tests, exactly how to write a really good test suite with nobody helping you. Nobody telling you which test cases to write, which ones you need to really test your code. Because when you get to 220, 250, they will still test some of your testing. They'll make sure you have some tests, but not nearly as much as I do in 116. But then after that, after 220, 250, I'm not aware of any course that's going to check your testing and require you to have testing. So especially by the time you get into the 300 level courses, 300 and 400 level courses, you need to have this skill. You need to be able to test your own code without anybody telling you how to test, what features to check. You need to be there. So I have to back off to make sure that you have those skills. As a result of all that, a lot of the questions for Task 8 are more related to the programming requirements. You get to the last phase of checks, and I say, your code didn't pass all of my tests. Because you actually do have a bug in your code, and you didn't write a test case for that bug. And I'm probably going to say, hey, you need more testing. Even though it's not required that you write more test cases, Autolab's satisfied with your test cases. That's by design because Autolab's backing off on that requirement. But if you get past the testing and failing the programming requirements, that means you don't have enough testing. Like you didn't get the point of testing at this point in the semester, which is kind of detrimental moving forward in your career. So you do have to you have to have those skills moving forward of figuring out what to test, how to test, because it will save you tons of time, absolutely tons of time. I also teach CSE312, and there are a lot of students who take that class who are like, well, testing's not required, I'm not going to do it. I'm not going to do any testing, because they won't do any testing after 116, 220, 250. And they end up spending hours and hours and hours of time banging their head against a bug that could have been fixed in minutes if they just wrote a test case or two. And I hate to see that. I don't like seeing students waste their time. This degree doesn't have to be all, time consuming, this black hole of time that takes over your entire life. It shouldn't be like that. It doesn't have to be like that. If you have good habits, if you have good testing habits, if you have good debugger skills that you've developed in these 100 level courses and the 200 level courses, and carry that throughout your career, this degree doesn't have to be, you don't have to dedicate your whole life doing each assignment. So I want you to have that skill. So you will see more programming requirement errors failing on my tests if you have bugs and you didn't test for those bugs. But that's by design of the assignment. So don't be shocked when that happens. As a side note, I'm considering requiring testing. It's such a big problem that I'm thinking of requiring testing in 312. And it's not that nobody tests in 312, but nobody who comes to office hours tests. I shouldn't say nobody. One or two students over years have I seen. But the students, I believe there are students who are testing their code, but they never show up to office hours because, they wrote tests, they ran the debugger, they found their bugs, they fixed their bugs. They never need me, which is where we need you to be. By the time you graduate, you shouldn't need the instructors or the TAs, because you won't have that out in your career. So anyway, that's task 8. Let's talk about how to do it. So with this one, I'm still not 100% decided, believe it or not. But I might go completely slides on this one. There's one point where I think I will go to the code at one point. But I am going to go mostly slides. There's only one slide in this, somewhere in here. One slide right here. This is the only slide that even has code on it. This lecture is very much a conceptual lecture. There's not much code that I'm even going to show. So I might, for this slide, go to the code and code this up live. We do have a little bit of flex time today. I even ended the first lecture early. I asked for questions, waited for a while for questions. Nobody had questions. Well, there was one question. I answered it, and then we just ended early. So there's plenty of time in today's lecture. I might code this up live, but I don't know if I see the benefit of doing that. I might still do it since we have the time to do it. And I would like to do some live coding. This is the live coding lecture, so I'd like to do some. But most of it will still be slides because it's conceptual. It's not something I can really do in a live coding format. And Paul still does this lecture. If you know the differences between our styles, like this lecture is the Paul teaching style. When Paul teaches this lecture, he basically, what's the way to word this? Students basically rely on watching my lecture because this isn't a lecture that you can really do with live coding. You can't really prepare students for how to do task 8 with live coding without just coding task 8 and giving them the code, which I'm not going to do, and which Paul didn't do. So the students pretty much just had to watch my lecture if they wanted the help on task 8. So it's going to be mostly slides because this lecture just doesn't fit the style. Doesn't fit that teaching style of live coding. Okay, so we're learning a new data structure today, graphs. And for some of you, this will just be review. If you've taken 191, or if you're taking 191 right now over the summer. I don't even know if it's offered in the summer, to be honest, but it should be. I think it is, but I don't know if it's the same first 6 week schedule like this one. So you might not have got to graphs yet if you're taking it this summer. But anyway, if you're taking 191, you've seen graphs. So graphs is going to be a bit of review for this first part of lecture. But I'm going to teach this lecture with the assumption that you have never heard of or seen a graph before. So I will take it from the top. But if you've taken 191, this should feel pretty comfortable until we get to breadth first search and distance, finding distance with breadth first search. That's where it's not going to be 191 review anymore. But let's get caught up on what a graph is and why we even need graphs. Like, we have 4 data structures already. Like, how many data structures is enough? Like, isn't 4 enough? Some people argue that 1 is enough. Like, I can do everything with an array list. Like, which is, it's an opinion. It's a decent one. You can do most things with an array list, but there are certain things that the array list is going to fall short. So why do we need even 4, much less 5 data structures? Well, let's compare the differences between them. The short answer is efficiency, which I'll have a little rant on, not rant, but a little tangent on later. But first, we have our sequential data structures. In Java, this is our array list and linked list. So we have 2 different sequential data structures which which remember the order of elements. We have elements in a specific order, and that's the sequential data structure's job, is to maintain that order, remember that order, and let people work with that ordering. Then we said, well, sometimes we have data where it doesn't really have any intrinsic order, but we want to map them and associate them with certain keys. So then we had our key value stores, which map values based on their keys. So each key has a specific value associated with it. And for certain applications, certain sets of data, this makes a lot more sense than just storing sequential data structures. So we can easily look up the value at a specific key, and it does deduplication as well. If we add CSE as another key in here, it'll just overwrite the value instead of adding another key value pair with the same key, which is a very handy feature in a lot of cases for certain applications. And then we saw our first nonlinear data structure, a tree, which had this branching property, which helped us represent certain types of data. For our application, we did a BST. It created BSTs, which stored values in sorted order very efficiently. We had log n runtime on our methods because of this branching structure. Each time we branch, we eliminate half of the remaining values, which is very powerful. It gets us to those log n runtimes for sorted data. And there are other applications of trees that we didn't see. Anything where you want this branching structure, like a decision tree, for like AI making decisions based on the available data. Each node will be a question, and then if it's yes, go right. If it's no, go left. And then eventually you get down to a leaf which says, take this action. That type of information, that type of decision making really lends itself well to this tree structure, this branching structure. So that's the data structures that we have so far. And then we're given this type of data. We're given data like the subway system in New York City, where we have stations and then trains connecting certain stations. We have road systems. We have intersections with roads connecting certain intersections. And we have the example that we'll use throughout this lecture, the early days of the internet, where we have certain locations that are connected through cables and are connected to routers on either end to be able to communicate over the early days of the internet. I believe at this point it was still called ARPANET, but this is what eventually became the internet as we know it today. This is the very start of it, back before it was called the internet. So we have this type of data, which importantly has what's called cycles in it. So we can go around a loop from node to node and arrive back at a specific node. We can, let's see if I can find a loop in here. Or cycle in here. So we can go around these cycles and arrive back at the original node. This is what makes this data more complex. So we're looking at the 4 data structures that we know so far, thinking about which one we would use to represent this data, and there's no real clear answer. We do have some branching going on, so it makes sense to think of a tree. So let's try a tree and try to represent this data as a tree, which is going to get us kind of close, but we're going to have some issues here. And let's pick some node arbitrarily for our root. I picked UCLA. And then each node that's connected to UCLA, we're going to have that as a child node of UCLA. And this isn't a binary tree because we can have more than two child nodes. We don't just left and right. We would have like an array list of nodes, node references. So an array list of child nodes. So UCLA is connected to all four of these: Stanford, SRI, RAND, UCSB. So those would be the child nodes of UCLA. And let's repeat the process for each child to get the grandchildren nodes, if you will. At Stanford, we have SRI and UCLA. So those are going to be the child nodes of Stanford, and we immediately have a very critical issue. So Stanford has UCLA as a child node because you can get from Stanford to UCLA. They are connected. But Stanford has UCLA as a parent also. So UCLA has a child of Stanford, which has a child of UCLA, which is going to have a child of Stanford, which is going to have a child of UCLA, which is going to have a child of Stanford, all the way out to infinity until you run out of heap space and everything blows up. That's going to be an issue. Debatably, you can solve this issue without too much work. You can say, well, Stanford has a parent, like each node would have to remember its parent, and then say Stanford has a parent of UCLA, so don't have a child of UCLA. Like, that doesn't make sense. So UCLA, get rid of that because it's already connected via the parent, which is fine. But we also have SRI as a child. So SRI is a child. It's not the parent node. So now we have a situation where Stanford would have to know about all of the other nodes in the tree and then not duplicate any of those nodes throughout the entire tree. Which is, to be fair, is what we're actually going to end up doing. But we have to be careful if we're building this as a tree to not have those duplicate nodes. So let's try something a little bit different. Let's just not duplicate any nodes. We're going to do what I said. We're going to look through the whole tree and say, if there's any node that's duplicated, when Stanford has UCLA and SRI, UCLA, they're already connected, so let's not worry about that one. SRI already has a node that exists, so let's have the child node refer to that node that already exists instead of creating a brand new node for SRI. So now every node has child nodes that it refers to, but we're not going infinite on the number of nodes because we're reusing the existing nodes and storing references to them. And now we have a different problem. So this is our graph. This is how we're going to represent our graphs. But we have a pretty big problem here still, is if we're thinking this as a tree still, because we could use our binary tree node code. We can't use our binary tree node code because we're going to have more than two children. But if we modify that to, instead of left and right, an array list of children, we can use our tree node code to represent this information. And that's fine. We're not going to do that, but that's fine. But then what happens when we want to do anything with this tree? Say we want to traverse this tree. We just want to visit every node. We pull up our pre-order, in-order, post-order, traversal, whatever one we want to use, and we run that on this graph. We start at the root UCLA, and we say, give me an in-order traversal. And we start making recursive calls. We make a recursive call to Stanford, and then Stanford is going to make a recursive call to UCLA. We can have some extra code and extra conditional that says don't go back to the node that made the recursive call and pass a reference to that node. We can do some stuff like that to avoid that one without too much trouble. But we're going to make the call to SRI. We're going to say, okay, let's go visit SRI. SRI is going to make a recursive call to UCLA. UCLA is going to make another recursive call to Stanford, back to SRI, and we're going to get stuck in one of these cycles. So this is the big difference between a tree and a graph, is a graph can have cycles, which is a list of nodes where you can travel from one node to another and get back to the original node. And we can omit the pass or the cycles with just two nodes in them, fine. But we're going to get stuck in some of these cycles. We're going to get stuck in some cycle like this, or even going all the way around the graph. We have to have some way for RAND to say, whoa, we can't go back to UCLA because that's a cycle. So we have quite a bit of extra code that has to happen to avoid this. And, I mean, that is what we're going to do. So we have to avoid getting stuck in these cycles because we're going to go infinite. We're going to get Stack Overflow errors if it's recursive, or just timing out if it's with a loop. you're going to get some type of error that's going to say, this is no good. Your code's broken. It doesn't ever end. So this is what we have to handle, because there's no leaves, which are nodes where all the child nodes are null, or it would be an empty array list in this example of child nodes. That's not guaranteed to happen. In fact, in this graph, there are no leaf nodes. Every node has a connection to at least two other nodes. So we're never going to have one of those leaf nodes. So our existing algorithms that we have for trees are all going to go infinite. We're just going to go in circles around this graph forever, and our code never ends. So we need new algorithms if we're going to use these graphs. We need more algorithms, not more, but different algorithms to work with this data in this structure. And before we get there, we have to represent our graphs in some way. And we're actually not going to use the representations that we have so far. In our linked lists and our trees, we had node classes, and those classes, objects of those class types, referred to other objects of that type, and we linked them together using those references, and that's how we built our node-based data structures. We're actually not going to do that with graphs. We could, maybe, but it'd be painful. I'll say it'd be painful. We just don't do that with graphs. Instead, we're going to store all of our nodes and edges. Graphs are all about nodes and edges. So instead of thinking this as a child relationship, storing a reference, we think of this as an edge, as its own kind of thing. So we have nodes, which are all of the, kind of the same idea of what we've used nodes for before. They're the things that store the actual values. We have nodes and edges, which connect the nodes. So nodes and edges, this is how we represent graphs. This is how you did or will do it in 191. It's how we do it in 116. It's how you'll do it in 250. It's how you'll do it in 331 if you're taking 331. If you're not, if you're a computer science major, not computer engineering. Or bioinformatics. I don't know if bioinformatics has to take 331. I don't recall. But you'll see it. This is just how we represent graphs, is node by nodes and edges. And specifically, the way we'll represent this in 116, I almost said the wrong course number. The way we'll represent this in 116 is through what's called an adjacency list. We're going to use an adjacency list to represent all of our nodes and edges, and it's going to look a little something like this. So our adjacency list is going to be a hash map mapping nodes to an array list of all the nodes that are connected to that node via an edge. So UCLA is connected to Stanford, SRI, UCSB, and RAND through edges. So in the adjacency list, UCLA gets Stanford, SRI, UCSB, and RAND in its adjacency list. So if you ever want to find all what we call the neighbors of a node, which are any node that's connected to a node by an edge, you go to the adjacency list, you say, give me all the neighbors of UCLA. You'll get an array list with these 4 nodes, and you can iterate over those nodes, do whatever you're going to do with all the neighbors of those nodes. And each edge is in this adjacency list twice, because we have what's called a bidirectional graph, meaning you can traverse the edges in either direction. So every edge is going to show up in this adjacency list twice. So UCLA connects to Stanford. Stanford is one of its neighbors. And if we look at Stanford, UCLA is going to be listed as one of its neighbors. So the edge connecting UCLA and Stanford is right here and also right here. It's going to show up twice. There is another way to represent graphs. We're not going to use this in 116, but you'll see it at some point in your career if you haven't seen it in 191 already. Is an adjacency matrix. Oh my god, if I bit my tongue. Is an adjacency matrix. The matrix doesn't like me at all. I can't even say it without hurting myself. Adjacency matrix is going to be like a spreadsheet or a matrix if you've taken a math class with matrices, where the rows are going to be the nodes and the columns are also going to be the same nodes, the same list of nodes. And then for each cell or each entry, you're going to have a Boolean value that's either true if there's an edge connecting those two nodes, or false if there is not. So it's a different way of representing the same information. With an adjacency matrix, you have a slot for every single possible edge, and then you're setting a Boolean value to true if there actually is an edge in connecting those two nodes. With an adjacency list, we're only storing the edges that actually exist. So if we don't have a lot of edges, this is more space efficient, but again, we're getting beyond what 116 needs to talk about. But adjacency list, usually more space efficient, since you're only storing the actual edges that exist. And you know what? Let's go to the code. I'd be a little remiss if we didn't do the code here. Let me create stash, and let's delete our graph and recreate it. So we want to do this. We want to create this in memory. We want a graph class. Let me just make sure the code compiles still. It might not, but it might. Okay, it does. So we want to create our graph class. The first thing I'm going to do is give myself a type parameter. I think we do n in the slides, and in the code I just deleted. N for node. As long as our type parameter is one single capital letter, that's fine. Remember, never actually name your type parameter. This is just asking for trouble. What did I say? N for node. One single capital letter. That's not going to conflict with any other names. And it's not going to be confusing. You know that that's a type parameter, and it's very clear what the purpose of that variable is. It's to represent a type parameter. So we want our graph to take a type parameter, so we can create graphs of any type. I'm going to create a graph of strings. Graph. So I'm going to end up creating, and we'll take some of the data from lecture and add it to this graph in our main method here. So to represent the information of this graph, we need an adjacency list. Adjacency list. And the type of that adjacency list, we need nodes to lists of nodes. It's going to be up for debate, I guess. Adjacency. I have errors, so it's not giving me my autocomplete. So the type of this, we want to map nodes to all of their neighbors. So I have a mapping that's going to tell me that I want a map, like a hash map. So I want some key value store. And I'm going to map nodes. So the keys are going to be the value matching the type of the nodes, strings in our example, and it's going to be strings on your homework too. So all the graphs you're going to see in this course will be graphs of strings, as it turns out. So I wanted to map those strings to lists of strings, to all of the neighbors. I need some data structure. I need one of my sequential data structures. I'm going to choose array list because they're a little less confusing to work with than linked list. So array list of n. So I'm mapping nodes to all of their neighbors. Get my imports in there, and then adjacency list is new hash map. Before I forget, good adjacency. See, so I will use. I say this all semester. I feel like I will use autocomplete like this. That was not AI assistance, notably. That was autocomplete. But I am always going to double check. So my type's right, get adjacency list. I like my capitalization there. Return adjacency list. The only thing I want to add is my this dot. So I'm going to make sure the code that I got was what I was going to type. I'm just saving myself keystrokes. I'm not letting the IDE do the thinking for me. Once the IDE does the thinking for you, you're out of a job. Just so you know, just putting that out there. You're no longer part of the process anymore, which means the company that's paying you no longer has to pay you six figures to just have the IDE write your code for you, or ChatGPT to write your code for you. There's a job crisis in tech right now. I suspect that's part of it. A lot of people are realizing that they don't have to pay you six figures if all you can do is use ChatGPT. Why would you pay an expensive developer to do that? It doesn't make sense. You need to be able to do the more complex stuff. If you can't do the more complex stuff, you're out of a job. AI is taking it over. Which I don't want to go down that tangent, but I will a little bit. We used to have these conversations in CSE142. I would have class discussions. They were some of my favorite lectures too, where we talk about ethics and AI and all that kind of stuff. And asking the class, like, what do you think about AI taking over people's jobs? And largely the attitude is, well, if AI can do your job, you're not skilled. Like, AI should be taking over those jobs. The conversation at the time was automating driving a vehicle. Like, it's going to put a bunch of truckers out of a job. And they're like, well, if all you can do is drive a truck, you should be out of a job. Like, that'd largely be the attitude. And I bring up, well, what happens when the day comes that AI starts taking your jobs and starts writing code for you? And they'd laugh and scoff. Oh, that's never going to happen. We're way too valuable. We're living that right now. Like, AI is starting to take over coding jobs, at least the basic ones. If all you can do is write really basic bullshit code, AI is doing your job for you, man. It's kind of scary, but at the same time, it's kind of exciting because we don't have to focus on, like, once you get past the basics, past 116, 220, 250, once you get past all that stuff, and the AI just handles all that kind of details for you, once you understand how it works, you get to focus on the more interesting stuff, the more interesting problems that requires a human to solve. So I think it's more exciting, but maybe that's just me. I don't know. I think you all should think that's exciting. Why else would you get into this career if you didn't want to solve challenging problems? But you have to be able to solve those more challenging problems. Okay, so I got on a little tangent there. I'm sorry. I didn't mean to go on that tangent. AI is just such a huge topic right now that we all have a lot of opinions about. Okay, so I have my getter for my adjacency list. And what I want is some way to add information to this adjacency list. I'm going to do this through an add edge. I'll stick with what's in the code in the repo and do add by directional edge. And I'm going to need two nodes. I'm just going to call them node A and node B. Actually, I'll actually say node B, just to make it a little more clear what my intentions are. And node A. Oh my. But anyway, with that tangent, just make sure you're double checking. If you're using any tools like that outside of coursework, you can use AI assistance. It's used in industry all the time. Just make sure you're careful about what it's doing for you. Make sure you're double checking what it's doing. And make sure you can double check it. If you're having it write code that you don't understand, that's when you're getting into really scary territory where you're less and less of the equation. That's what I mean with the scary stuff. If you know what it's writing and you're just saving keystrokes, good on you. Use the tool. Not in a course. Well, if you understand what it's doing, though, maybe that is fine. I don't know. It's all new territory for all of us. This is going to return void. And I'm going to write a helper method here. So when I add an edge, I can't just add the edge. So what I want to do is this dot adjacency list dot get, and I'll explain this line in a little bit. I'll explain this more. Node A dot put, because it's not a complex line, but there's enough going on that it's worth a reminder. Node oh, it's complex enough that I'm messing it up. Add node B, and then this dot adjacency list dot get node B dot add node A. So what I want to do is add this edge into my adjacency list. So in the adjacency list for node A, I want to add node B into that array list, which will be its adjacency list. And then for node B's list, I want to add node A as a neighbor of node B. So I want to get this edge in there twice to be able to represent that I can go in both directions. That's why it's a bidirectional edge, that I can go in both directions with this edge. The problem with this is going to give me all kinds of errors. Well, actually, since we have our method here, we can show that off. Graph dot add bidirectional edge. UCLA Stanford. UCLA. I forget exactly what the nodes were from the slides, but let's get some nodes in here. Let's run this, and we expect some errors here. So we got a null pointer exception in tasks 3 and 5. A lot of you have seen a lot of these. So I have a null pointer exception right here. It says can't call get, or can't evoke add because get return null. So get return null. So this resolved to null, so I can't call add. Once I hit the dot operator, I'm trying to ask null to take me to your object. That you can't do that. That's an error. Not going to work. So we can't do that. And the reason this is null, get node A is null, is that node doesn't exist. That key doesn't exist in this hash map. Actually, I thought this would give a key error. This doesn't give a key error. It just returns null, apparently. I feel like I get key errors all the time with that. But anyway, you get an error regardless. It doesn't matter which one. You get an error because this doesn't return anything. So let's make sure we're initializing our adjacency list. And I like to do this in a lazy way. So I'm going to create a helper method that's going to add nodes to my adjacency list. So if I'm seeing this node for the first time, I want to initialize my adjacency list to get my initial key value pair in there. So if I add a node for the first time, I want to say this dot adjacency list dot put this node to a new array list. So I want to initialize that array list to a new array list if this is the first time I've seen this node. Now the way I have this written, and I didn't finish writing it, this dot add node, I never called my method, node A. So I want to add my nodes. Oh my. Add node B. I want to add my nodes, so I'm initializing the array lists to empty array lists. I'm initializing my adjacency list to give new array lists for these nodes. Now I don't get any errors when I run this code. But I do have an issue with the way it's written. I'm going to add these nodes every time they're added. So UCLA is going to get, let's get a little debugger action here. So UCLA in Stanford, we're going to add this edge to our graph, and we're going to lazily, I ran it instead of run the debugger. We're going to lazily initialize the graph. So when the graph is first created, I'm going to do step over. I don't want to click through every little click here. Our graph has no adjacency list. It has an adjacency list, but it has nothing in it And then every time I see a node for the first time through the add bidirectional edge method, I'm going to initialize its array list. So after adding this edge, my adjacency list is going to have two key value pairs, UCLA and Stanford, each with edges to each other. So my adjacency list has Stanford mapping to UCLA, just one value in its array list, and UCLA mapping to Stanford, one value in its array list as well. Now when I hit the second bidirectional edge, what's going to happen is I'm going to reinitialize Stanford to a new empty array list, and I'm going to lose some information. So I'm going to skip over the whole call, but I'm going to look at the aftermath. Stanford no longer has UCLA. Oops, I'm supposed to be looking at UCLA. UCLA no longer has that edge to Stanford. Stanford still goes to UCLA. UCLA doesn't go to Stanford. I'm missing information in here because I wasn't careful with the way I'm initializing things. This is a common situation in task 6 when you see a rating, two ratings for the same song, making sure that you're not erasing the first rating when you add the second one. It's similar situation. We want to make sure we're only initializing one time, only the first time we see that song, the first time we see that movie, the first time we see this node. So what I'm going to do is add a check here. If this dot adjacency list dot contains key node, so if this adjacency list has this node as a key, then I do not want to initialize it. But if it doesn't, then I do. So if this node is not in the adjacency list, then initialize it. And now if we rerun our debugger, I'm going to just step over the method calls to get to where we were. Now my adjacency list for UCLA has size 2, and it correctly has Stanford and SRI as the neighbors of UCLA. SRI, same thing. We're going to have UCLA and Stanford as the neighbors of SRI in our adjacency list. Then MIT and Lincoln, they map to each other. They're the only edges between the two. And by the time we're done, we have all of our nodes as keys and then mapping to array lists with all of their neighbors, which is exactly what we want out of this graph. Which brings us back to the slides. So that was this. I think I did this exactly. A instead of in node A and node B in node. So little variable name differences, but I recreated pretty much the exact code, and I didn't add all the edges here. The code that's given also has this add edge method. This is, for our purposes, for task 8, this add edge method is not going to be useful. This is to add a directional edge, meaning an edge that you can only go from the first node to the second one. That's not going to be the case in the homework because of the nature of the setup of degrees of separation. It's always bidirectional edges. If you're in a movie together, it doesn't make sense for one actor to be in a movie with another and that other not being in the movie with the first one. If they're in a movie together, they're both in the movie with each other, so it's a bidirectional edge. Okay, and we're back to slides because, again, that was the only slide with any code. Doesn't really make sense to go back to the code unless I just want to code random examples, which I might. I don't know. I think I'll do the same thing that I did in the last lecture. I'll get to the end of the slides. I don't plan, just to give you a heads up on this, what I'm going to do at the end. The third slide deck is just a memory diagram. And you're not asked to do a memory diagram on graphs. So I don't think it's super useful to go through this. I'll do it on demand. If anybody asks for it, I'll go through it still. But my intent is to go through the first two slide decks here And once we get to the end of the second one, I'll open it up, leave it up to you, whatever you want me to do. I'm at your mercy at that point. Whatever you want to see, whatever questions you have, questions on the tasks. If you do want to see the memory diagram, anything anybody wants to see, I'll take requests until 1:30 is when lecture ends, right? Yeah. Until 1:30, I'll take requests, and if there are no requests, I'm just going to shut lecture down a little bit early. And we'll start our summer a little bit early. I'll still go to office hours, so it's not like I'm just bailing. But I'll end the lecture portion a little early. Okay. So that means it slides from here on out. And then if we get to the end, if somebody wants to see some live coding or whatever, it'll be by demand. Okay. So back to slide mode. We have to get a definition out here. A path in a graph is a sequence of nodes where every pair of consecutive nodes is connected by an edge. That's a path in the graph. So this path, this list of nodes, UCLA, SRI, connected by an edge, Utah, connected by an edge, MIT, connected by an edge, BBN, connected by an edge, RAND, connected by an edge. This is a valid path in the graph because each pair of consecutive nodes is connected by an edge. This sequence of nodes, SRI to Utah, connected by an edge, Utah to BBN, there's no edge here, so this is not a valid path in the graph because they're not all connected by edges. There's no way to get from Utah to BBN without going through MIT. It's not a valid path. If we added MIT in the middle there, then we could turn it into a path. This is not a path in the graph. Which brings us to breadth first search. That's the structure of a graph, just like linked lists and trees. Talking about the structure doesn't take super long. I guess that did take 50 minutes. That took a whole lecture period. But we're ready to talk about algorithms, which is actually a good moment in lecture to check out this question, because I have a feeling this won't be related. I have a question. If I passed one of the OP quizzes and didn't pass one of the DS quizzes, I would have to pass one of the DS quizzes on the final to pass the class, correct? You passed one. Yes, that is correct. So if you passed one of the OP quizzes, but you failed both of the DS quizzes on the midterm, then you do have to show up to the final to pass one of the two DS quizzes. But on the final exam, you would not be taking any OOP quizzes, so the two OOP quizzes you can ignore and just focus on the two DS quizzes. That's the only thing that you would need are the DS quizzes, the data structures quizzes. And you'd have to get one of those two. So make sure you're studying. You have the midterm DS quizzes and the sample DS quiz. Make sure you're studying all three of those. And if you have any questions about them, come to office hours. We can walk you through the traces, go over whatever mistakes you made. We can help you with that. And I'll give you the same kind of heads up that I did for the midterm. Is the final is going to look very similar to the midterm. It's going to look like different versions of the same traces. So there will be some small changes, but it's going to test the same concepts. There's going to be a tree trace, which will look very similar to the one on the midterm, which was very similar to the one on the sample quiz, and then a linked list one, which will look very similar to the midterm. So study those three traces, and you will be in good shape. If you understand all three of those, you're gonna be great. You're gonna do great. I don't like seeing somebody, especially if you get all 8 tasks before the final. I don't want to see anybody failing on the final exam. Prepare, study those 3 things. Come to office hours for extra help understanding them, and we'll get you through that final. Okay, so breadth first search and connected component. So connected component, another definition. Connected component is a set of nodes that are all connected to each other by a path. If the entire graph is one connected component, like is the case here, then we say the entire graph is connected. The graph that I coded in IntelliJ just now had 2 connected components because Lincoln and MIT were not connected to the rest of the nodes. And we can simulate the same thing here. If I remove 2 nodes from this graph, these 2 are 2 edges from this graph is now no longer connected. There are 2 connected components to this graph, this clump of nodes here and this clump of nodes here. So my first question is, how do we tell if two nodes are connected? Like, our eventual goal is to figure out if the distance between two nodes. We haven't even defined distance yet. But before we even get there, how do we just tell if two nodes are connected to each other? So for the homework, if two actors are not even connected to each other, if there's no way to get from one to the other, then our task is to return -1. They're not connected. Their degrees of separation is effectively infinity. Not connected, return -1. So let's at least start with this edge case. How would we even handle that? Let's start with a simpler question, then we'll work our way up to finding the distance between two nodes. We're actually going to go through the run of breadth first search 4 times in today's lecture. So this is the first one. This is going to be the most vague one. And then we're slowly going to add in more details to get you to the point where you can do task 8. So for this one, we can just look at this graph. If I give you any two nodes, you're just going to look at the graph. And you're going to tell me if they're connected or not. You're just going to eyeball it, right? But the internet's gotten a lot bigger since then, since the very early days of ARPANET. It's gotten a lot bigger. This is the internet now, or not now. This was years and years ago that this graph was generated. This is a lot more complex. You're no longer going to eyeball. If I say this node and this node here, are they connected? That's going to be tough to answer. And especially once I say, what's the distance between those two nodes? You're going to have a very hard time just eyeballing that. By the time you give me the answer, it's not going to be relevant anymore. The whole internet's going to be shaped differently by that time. So we want an algorithm that's going to do this for any general case. An algorithm that's going to handle this graph and an algorithm that's going to handle this graph just the same with the same code. And this is the reason to write code. This is the reason for data structures in general, the reason to have 5 data structures and many more that you're going to learn throughout your career. It's the reason to not just say array list for everything. With data structures, it's efficiency. If you have a really sloppy algorithm and you give it this graph, it's not going to run in any reasonable amount of time. In fact, for task 8, I had to remove my test case that uses the entire movies.csv file because too many students were timing out in Autolab because their code was really slow. They were using the wrong data structures in the wrong places and just really sloppy, slow code that would end up hitting the 3-minute timeout in Autolab. 3 minutes is an eternity for an algorithm of that size to run. And I ended up just removing the test case because in 116 we're not really concerned about efficiency, but in 250 you will be. 250 is going to teach you how to choose the right data structure for the right problem, which is all about efficiency. And I'll go a step further and talk about computers in general. If this is your test case, if this is the data that you have, you shouldn't even be using a computer. Like, you should sketch this out on a piece of paper, and if somebody says, are these two nodes connected, or what's the distance between these two nodes, just do it by hand. That's going to be so much simpler than writing the code that solves this problem for you. Computers are only really interesting and only really useful when you have a lot of data. When you have movies.csv, songs.csv, the movie ratings.csv, when you have lots of data. If you don't have lots of data, don't even use a computer. But if you have lots of data, that's when you're taking advantage of the strengths of this tool that we have, the computing power of a machine. Because what computers do really well is crunching a lot of numbers really fast. We measure processors in terms of gigahertz. That's billions of operations per second. Your human brain cannot do that. Billions of operations per second. And they crunch numbers really fast. They store large amounts of data. They store it perfectly with 100% accuracy down to the bit, aside from hard drive errors and any hardware errors that you might encounter. Sometimes they forget when you have an actual hard drive error. I think that's the only 2 I got. I thought I had 3. But they can crunch numbers really fast, and they can remember things very well. Oh, and crunch numbers with 100% accuracy. They're never going to make a human error. They're never going to just make a mathematical error. I mean, again, aside from really strange things, solar flares flipping random bits and stuff like that, but they're damn near 100% accuracy with 100% perfect memory, with large amounts of memory and huge amounts of data being processed every nanosecond. Really, lots of data being processed. So if we're not playing to those strengths, then a computer isn't even the right answer. So everything we learn in computer science, which we can't really get in 115 too much, and we can get a little bit of it here in 116 towards the end, but 250 forward for sure, where we have to play to those strengths of the computer, or else there's no reason to use the computer. Or I guess communication, I should add to that. A computer can talk to another computer all the way around the globe in less than a second, which is just incredible, absolutely incredible. So communication too, I'll add to that. With the internet these days. So we have to be playing to those strengths. So our algorithm needs to be able to work with this graph, or else there's no reason in studying algorithms, because that's their strengths. So in case you've lost sight of what the hell we're even doing in computer science, that's what we're doing. When we have lots of data and we need a lot of numbers crunched really quickly, and machines communicating with each other. In 115, 116, you really haven't gotten to the networking part of things yet. So that one's not super relevant to you right now, but it will be. Okay. So we will use this toy example in lecture, but that's just to show you the concept. Just keep in mind, if you're like, well, I can do all this stuff with this graph super easy, just keep in mind that our goal is to write an algorithm that's going to work for the other graph and any graph ever in existence, even if it has billions of nodes. Our algorithm should still work. Our code should still work just fine. If we give your solution to task 8, if we give it every single movie ever created with their entire cast list, which the movies.csv file is significantly trimmed down. I had to deduplicate any movie with the same title. I also got rid of any movie with less than a certain number of actors. I forget what that number is now. Any movies that contained an actor that was only in that movie. There were a lot of things I did to trim that down so the file isn't completely cumbersome. So it's easier to test with it. But if you were given the full original file, your code should still work just fine. Same code that'll work for this graph should work for that graph too. Okay, with that, let's get on with it. Breadth first search. So what we do for breadth first search is we're going to choose a node as our starting node and then explore all the neighbors and repeat. So I'm going to choose a starting node. I'm going to choose UCLA as my starting node. Your starting node for task 8, you're given 2 actors. You need to find the degrees of separation between them. Your starting node is either of those 2. It's not going to matter which one you choose. Choose one of them. That's your starting node, and then run breadth first search. So we're going to choose a starting node and then explore all the neighbors of the starting node, neighbors being any node connected by an edge. And this green box is going to mark all of the nodes that have been explored. And then I'm going to explore the neighbors of the neighbors. So all the nodes that I've just explored, I'm going to explore their neighbors. And I'm going to be careful whenever I'm doing that. I'm going to be careful to not re-explore a node that's already been explored. So I'm going to explore their neighbors, Utah and SDC. Then I'm going to explore their neighbors. And when I explore the neighbors of Utah and SDC, the neighbors that were just added in the last round, there's no new nodes to be added. Everything has either been explored or is not connected to Utah or SDC. So once I have a round of this where I don't add any new neighbors, then I know I'm done. And we're going to have some way to make sure that we don't visit a node twice, or else we'll get stuck in an infinite loop like we would with our tree traversals. If we ran a tree traversal on a graph with a cycle, we would go infinite. So we're going to make sure we don't visit a node twice, so we never go infinite. And now we've found the connected component of UCLA, which is the connected component of any of the nodes in this connected component. No matter which one of these we chose as a starting node, we'll get the same connected component. And if we chose one of these nodes down here, we would get a different connected component. So we could find the two connected components of this graph by running breadth first search twice. So if you were asked to find the degrees of separation between UCLA and MIT, you would start at one of those as the starting node, run breadth first search, and if you never explored the other one, which is the case here, then you know that those two are not connected. If you did explore the other node, then you know that they are connected. I'm skipping this slide. This slide is just motivating, like this is the end, would be the end of a Monday lecture. This slide is motivating the Wednesday lecture, but we're about to do the Wednesday lecture, so I don't have to motivate it at all. So more details to come right now. So let's give that more detail. So because with that first run of breadth first search, it's very vague, very hand wavy, very just explore the neighbors of the neighbors. We need to get to the point where we can do that in code. I'm going to have one more run that adds a little more background, and then the third run is going to be the one that's going to be most important to your homework. And I'll have a fourth like bonus run that I'll show you something else. I'll do pathfinding with the fourth one. Before that, a few more definitions. Paths we saw, but paths have lengths. So the length of a path is the number of edges in the path. So this path, 1, 2, 3, 4, 5, 6 edges, that's a path of length 6. Or it's the number of nodes minus 1. So 1, 2, 3, 4, 5, 6, 7. We have 7 nodes, minus 1 is 6. This is a path of length 6. So paths have lengths. And then distance, finally we get to introduce distance. So we saw a path from Lincoln to SRI of length 7. The distance between any two nodes is the length of a shortest path between those two nodes. So Lincoln to SRI, we have the path of length 7, that's fine, but there is a path of length 3 right here. So since we can get from Lincoln to SRI using a path of length 3, the distance between those two nodes is 3. And we can try all day. We're never going to find a path from Lincoln to SRI that's less than 3. We can't get there in 2 nodes. It's never going to happen. We're definitely not getting there in 1 node. There's no edge connecting them. So 3 is the shortest path in this case. I'll say a shortest path in case there's a tie. We're going to see Carnegie to MIT. There's 1, 2, 3. 1, 2, 3. There are 2 shortest paths. So as long as we're looking at the length of a shortest path, that's the distance of a graph. Rand and BBN, these are connected by an edge. If 2 nodes are connected by an edge, their distance is 1. There's only 1 edge we have to take to get from one to the other. And one of our edge cases is the distance of a node to itself is going to be 0. We don't have to take any, the path is just Rand in that example. That's a path with 0 edges. And the number of nodes, 1. The number of nodes minus 1 is 0. The distance is 0, a node to itself. And distance is what we want. This is what we're after. So in the homework, your nodes are going to be the actors. You'll create a graph of strings. The nodes are your actors. And there's an edge between 2 nodes, an edge between 2 actors, if they've starred in a movie together. So for each movie, every pair of actors in that movie, you add an edge between them. Do that for every single movie. That generates your graph. And that graph is set up in exactly the way you want it to be, such that distance between 2 actors in that graph is exactly their degrees of separation. So if the degrees of separation definition is a little confusing to you, it's kind of iffy with you, create your graph and then just think of it as distance. You're just returning the distance between 2 nodes in a graph. It happens to be the degrees of separation between actors in movies, but it's going to end up being computing the distance of nodes in a graph. And that's what we're going to focus on for the rest of the lecture is how do we find the distance of 2 nodes in a graph? Now that we know what distance even is, the length of the shortest path. And we're going to use breadth first search to do this. Breadth first search is the only graph algorithm we're going to study, actually. So hopefully that's the answer, because that's all we got. So we're going to use breadth first search to find this distance. And let's do our second run of breadth first search and figure out how breadth first search is even useful for this. Like how are we going to use breadth first search to get these distance numbers? So let's run breadth first search again. And I'm going to start at Carnegie this time, just to switch things up again. We're going to start with Carnegie for the next 3 runs of breadth first search. So I'm going to start with Carnegie. And instead of just running through breadth first search, just saying explore the neighbors of the neighbors and the neighbors of the neighbors of the neighbors and etc. Instead of doing that, I'm going to do that, but I'm also going to create another graph. I'm going to create another graph where I track all of the edges that I use to explore nodes. And I'm going to draw this in a very specific way. My start node, I'm going to put at the top of this graph. And whenever I explore a new node, I'm going to draw it visually lower on my new graph. So Carnegie is going to explore Case and Harvard. So I'm going to draw Case and Harvard down, going down when I add these edges to the graph. And I'm only adding the edges that I used during the run of the algorithm. So when I explore the neighbors of Case, Carnegie is already explored, but I find Lincoln. Lincoln's going to be below Case, and BBN is going to be below Harvard. So I had another edge that I used to find each of these, and I'm going to draw them lower on this new graph. And now I have a situation here where Lincoln can find MIT, BBN can find MIT. Only one of these nodes is going to find MIT, is going to explore MIT. Either Lincoln is going to find it, and then BBN's not going to go there because we never visit a node twice. We never explore a node twice. Or BBN's going to get there, and Lincoln's not going to find it because we don't explore it twice. So for this demonstration, I just have to pick one of these arbitrarily. I'm going to say that Lincoln will find MIT. It'll balance my graph over here a little better. Lincoln's going to find MIT. BBN has to find Rand. There's no choice there. So whenever you have a tie like that, you can break the ties arbitrarily. But when we get to the code, we're going to see that I'm not going to show the code for this. But when I get to the next run of breadth first search, we'll see that those ties are just going to be broken by your code arbitrarily. You don't have to write any extra code, but when I'm making a slide like this, I just pick whichever one. Either way, everything that we need out of breadth first search is going to be the same, whether BBN finds MIT or Lincoln finds MIT. But what's important is that only one of them finds MIT. So I chose Lincoln to find MIT, and then BBN does not find it. So this edge will not show up in my graph here. It's not going to be there. MIT finds Utah. Rand finds 3 separate nodes. So add those all to my graph over here. Again, going lower each time I traverse a new edge. And then SRI has a 3-way fight. UCLA, UCSB, and Utah could all find SRI. I chose Utah for this, and then UCLA is going to find Stanford. And then all these white edges were never used to explore a new node, to find a new node, so they don't show up in my resulting graph over here. And what we're left with is a tree. So a tree is a graph with no cycles. The relationship here, like every tree is a graph, but not every graph is a tree. It's kind of the same thing we've seen before. Squares and rectangles, game items and health potions, same kind of idea. A graph is a tree that can have cycles. So every graph with no cycles is technically a tree, theoretically a tree, even if we represent it with the graph class. In the world of theory, it is a tree if it has no cycles. So we have a tree, no cycles in this thing. And it's got levels. So the way we drew these visually lower every time we traverse an edge, if we label these as levels, starting at the root of the, root, if I'm going to call this a tree, starting with the starting node as level 0, and then each time we traversed a new level, every time we went down, every time we traversed an edge, we call that the next level. Level 1, then traverse another edge, level 2, level 3, level 4, level 5. If we label these levels like this, what we end up with is the property where the level number for a node is exactly its distance from the starting node. So every node in this graph, whatever level it's on, that's its distance to Carnegie. So the distance between Carnegie and UCLA is 4 because UCLA is on level 4. And the path that we have to find UCLA is a shortest path from Carnegie to UCLA. There might be multiple shortest paths, and that's where our ties were broken arbitrarily. Like Carnegie to MIT, this was our first tie that we had. 1, 2, 3. We have a path of length 3. If BBN explored MIT instead of Lincoln, it'd still be 1, 2, 3. So our structure would be a little different, just that we would choose different edges, but we would still get the same levels and find the same distance values for every single node. And that's what we're after. So the ties didn't matter. Breaking the ties didn't matter because we'll still get the same distance numbers. And that's what we're after right now. If there were some other application where we cared about more than just distance and there's something else at play, maybe we would care about how the ties were broken. We only care about distance, so ties broken anyway is going to be fine. Kind of a side note, but every edge that's not in the graph will connect to levels that are separated by 1. We'll never have an edge that's missing that spans 2 levels. Like there could never be an edge between Harvard and MIT because that edge would have been taken when we explored Harvard. It would have put MIT up on level 2. Kind of a neat property of BFS. And it's the reason why your test case that has multiple paths, those paths should differ by only 1 distance. So in Carnegie to SRI, for example, distance 5, we can stare at this graph all day. Carnegie to SRI, we're never going to find a path of less than 5 between those two. It's never going to happen. I can guarantee that because that's what breadth first search tells us. Breadth first search will guarantee there is no path less than 5. Now we broke some ties here, so there are multiple paths. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have multiple paths of length 5, but we're never going to find a path of length less than 5. We're never going to find that path of length 4 from Carnegie to SRI. It can't exist because if it existed, breadth first search would have found it. Since breadth first search didn't find a path shorter than this one of length 5, there's no way it exists. It can't exist. Not allowed. Not allowed to exist. Breadth first search says no way. So breadth first search does exactly give us the distance between any two nodes, or not any two nodes. The distance from the starting node to any other node in the graph. So for your homework, as long as you choose a starting node that's one of the 2 actors that you're interested in, choose one of those 2 as your starting node, run breadth first search, and then whatever level the other node was on, that's your distance. Which gets us close to being able to do task 8. But we're not quite there. We're not there yet. Because there's a big problem with this, the way that I just went through that run of breadth first search. Big problem is I kept saying, draw the nodes visually lower on the slide. But how do you do that in your code? Like, how are you going to visit a node and draw it lower in your program? Like, that just doesn't make sense unless you do all kinds of image processing and visualization and all kinds of really advanced stuff, which we're definitely not doing here. It's not practical. Like, it's not something we can do in our code. So we need a way to track these distances in a more code-friendly way. So this is going to be the 3rd run of breadth first search, and this is the most important one. If you're just trying to get through the homework, this is the one to pay attention to. This is where I pretty much walk you through and hold your hand exactly how to do task 8. And if you follow this, turn what I explain here into code, that's your task 8. That's how you're expected to do task 8. I really tell you a lot of the details of how to do it. So, how do we track the levels, which I'm just going to call distance from now on? How do we track those distance values in our code? So let's run breadth first search a third time, and this time I'm going to walk you through how to set up the code using 3 different data structures. This is where I get excited about graphs, is like the capstone for data structures in 116, is we get to use a lot of data structures to represent graphs. We already represent our adjacency list using a hash map and an array list, and now we're going to use 3 more data structures, which will be more, this will be a hash map, an array list, most likely, and then this one will be a queue. So we're going to get queue in there as well. We're going to have 5 different data structures that we use, all combined together to solve one problem, which makes it a pretty good capstone for data structures. So we're going to use 3 data structures here, and I'm doing these a little out of order of my slides because this is the order I want to explain. I got to reorder my slides someday. The first one is a map, which just seeing this sure looks like key value pairs. You should be thinking map when you see a structure like this. But a map that's going to map each node to its distance value, its distance from the starting node. So with this one, I initialized, for the slide, I initialized all of my nodes, and I initialized it to infinity for each node, just to represent that we haven't explored that node yet. I do this for the slide just so I have my entire hash map here. It looks better visually instead of resizing it. But in your code, if you create a hash map and just add only the nodes, only the key value pairs that you know about, instead of initializing these to infinity, you add the key value pairs for the first time when you're ready to actually have some values to add. That's fine. That's what you can do in the code. I think that's what I do in my solution too. I don't think I initialize everything like this in my solution code. But you're going to create a hash map. This is going to store the actual distance value for every single node. And we're going to initialize the start node because we know its distance. A node's distance to itself is always 0. So the start node's distance is 0. And that's the only thing we know right away. That's the only thing we know so far, is the starting node is distance 0. Then we're going to have a queue, which is going to track the nodes that we're going to visit the neighbors of. This is going to keep track of the order in which we're going to visit these nodes and explore the neighbors, and it keeps track of all of the bookkeeping, all the ordering. I already said that word, but that's what it does. It keeps track of the ordering in which we're going to visit nodes in such a way that all of the properties that we want out of this run of breadth first search is going to be kept track of through this queue. So this queue, we're going to enqueue the starting node. We're going to initialize it as the starting node. And for the queue itself in your code, you have some options in how you represent this queue. You can use the queue that we built in lecture that's in the examples repo. You can use that one. You can use Java's built-in queue class. You can use a linked list and just use it as a queue, basically rebuilding the queue that we have in lecture. You can use an array list as a queue, as long as you use the first in, first out concept. You can use an array list or a linked list, however you want to do it, but you need the concept of a queue in your code. And if I were to give a recommendation, the easiest one's probably Java's queue, Java's built-in queue. If you use the one we built in lecture, we built like a true, just raw queue. It has enqueue and dequeue. But we will have the need to check if the queue is empty. So, you can do it with that queue by popping and seeing if it returned, or dequeuing and checking if dequeue returned null. So it's not too hard to do that. But Java's built-in queue just has an isEmpty method. So it's not a strictly a plain queue. It has some extra functionality, but that extra functionality can be useful. But at any rate, you need some first in, first out data structure here. And initialize it by enqueuing your start node. And then the third and last data structure is something to remember which nodes have been visited. And this is the data structure that's going to avoid our infinite loops. We're going to remember which nodes have been explored. Or I use explored and visited interchangeably, but we're going to use this to track which ones have been explored. And I'm going to mark them in orange on the slide. So any node marked in orange, I know has already been explored. For this data structure, the probably the most proper data structure to use here is a set, but that's something I haven't talked about at all in lecture. But a set is going to do what we need it to do very efficiently. So we need to add values to it and check if the data structure contains a specific value. And set just does both of those things very efficiently. Most of you and most students in the past will end up using an array list, to the point where in my slides, when I'm going through this, I'll often refer to this as an array list, just because that's probably what most of you will use. An array list does have a .contains method, so if you want to check if an array list contains a specific node, add it to the array list when you explore it. If you want to check if it's explored, .contains, it's going to check it for you. It's going to be an O of n operation, so it's horribly slow. And a set, I believe Java's set is, actually I think set's an interface. You would create a hash set, which is going to be O of 1 to see if it contains a value, and O of 1 insert. So it's optimal for this situation. So set's the one you would want to use, but this isn't 250, it's 116 where we're not concerned about runtime yet. Most of you will use an array list, and that's what causes me to not be able to use the movies.csv file. An array list is going to be slow enough that you will feel the runtime. If you run it on movies.csv and run it in IntelliJ, it's going to be pretty slow. It's going to be slow. But it will get the job done. Will there be office hours next week? The schedule might change a little bit, so make sure you check the schedule to see if any of them are canceled. But there will, in general, be office hours. I don't even know what I'm doing with my office hours quite yet. Right, Tuesday. No, Tuesday's the 2nd, right? Yeah, Tuesday's the 2nd. Yeah, I'll have my Tuesday office hours for sure. My Thursday, almost certainly not. On the 4th. I'm not even supposed to have office hours because it's a holiday. And I probably won't because I'll be busy all that day. But I'll have mine on Tuesday. Plus on Thursday, what's that? Thursday is... Oh, it's before the test 7 and 8 final deadlines, but it's past the late deadlines. I mean, nobody should still be working at that point anyway on Thursday. If you're waiting until Thursday to finish up your tasks, I don't know. I'm not going to be there to help. But that said, especially coming up to those last final deadlines, I'll check Piazza to see how it's going, because I'll be kind of stressed out seeing who's going to pass and not. So I'll be on Piazza at least. Yeah, I should, right after this, I should probably cancel my Thursday. There's no way I'm going to make my Thursday office hours. Maybe I'll have some different office hours at different times since there's no lecture. But yeah, I'll have my Tuesday office hours after the final. Okay, and we're going to initialize this data structure with the starting node. So the starting node is already marked as explored. The starting node is in our queue. The starting node is in our distance hash map with 0. And then at that point, we have all 3 of our data structures all set up and initialized. And now it's time to run breadth first search. So this is our starting point of breadth first search. And then we're going to enter a loop, a big old loop. What we're going to do, what we're going to do is loop until this queue is empty. Once this queue is empty, we're done. But we got to loop until that queue is empty. And what we're going to do on each iteration of that loop is this. We're going to dequeue the front of the queue. We're going to take this node and we're going to explore its neighbors that have not been explored already. So the way we do that is we dequeue Carnegie. We're going to go to our adjacency list. We're going to say, give me all the neighbors of Carnegie. That gives you an array list of all the neighbors. And you're going to loop through all of those neighbors. And for each neighbor, you're going to check if it's been explored. If it has not been explored yet, so you're going to look in your array list here and say, does it contain this neighbor that I'm currently checking? If it does not, you're going to mark it as explored. You're going to add it to the queue. Where do we access office hours? Dude, it's the last lecture. You're asking that now? Holy moly. Go to the course website. Towards the top of the course website, the Piazza link takes you right to the Piazza post with all the office hours information. We're going to mark it as explored, enqueue it, and mark its distance as the distance of the node that explored it plus 1. So, and same thing for Harvard. Harvard has not been explored. Mark it as explored, enqueue it, and mark its distance as the distance of the node that explored it plus 1. And then that link has a link to the Zoom meeting. That post has a link to the Zoom meeting. And that's it. Then we repeat. We do the same thing until the queue's empty. So we're going to dequeue case and check all of its neighbors. Lincoln has not been explored, so we're going to mark it as explored, enqueue it, check the distance of case, which is 1, add 1 to it, and Lincoln's distance is going to be 2. Then case is going to explore Carnegie, because the array list is going to contain every neighbor. Every single neighbor of this node, which will include Carnegie. And this is where we have to make sure we're avoiding our infinite loops, and this is where our array list that's marking what's been explored comes into play. We're going to check, has Carnegie been explored yet? The answer is going to be yes. It's already been explored. It's marked in orange on the slide, which means it's in your array list that marks what's been explored. So what you do is nothing. You just skip it. Since this neighbor's already been explored, you don't want to do anything with it. Once a node's been explored, and once you have its distance number here, these distance numbers are final. You're never going to update these. You would never ever want to update a distance number. Once you find the distance, that's the distance. Which we know, Case and Harvard, their distances are 1. We don't want to change that. That's the final answer. When we explore Lincoln, its distance is 2. Carnegie, Case, Lincoln, we know its distance is 2 intuitively. And since the distance of Case, in general, in the general situation, the distance to Case from Carnegie is going to be whatever's in the hash map, which is 1. So if the shortest path from Carnegie to Case is 1, and using one more edge, I can find a new node that has not been explored, then I know it's 1 to get to Case and 1 more to get to Lincoln. So that's why we're always adding 1 to that value, because in 1 more edge, we can get to Lincoln. And we know Lincoln isn't any less than 2, because if it was less than 2, it would have already been explored when it explored the neighbors of Carnegie. And that's what breadth first search is doing. The way we have things set up, specifically with the queue, keeping track of the order in which we visit the nodes, that's going to make sure that we're visiting the nodes in the right order, that these distance numbers will be the final numbers whenever we visit a node. And we're only visiting a node exactly once. If we see a node's already been explored, we never explore it again. We're not going to a node twice. So this is going to give us our distance numbers. Harvard, same thing. Check out Carnegie. It's already been explored. Do nothing. BBN has not been explored. Mark it as explored. Enqueue it. And set its distance equal to Harvard's distance plus 1. So BBN is 2. And here we get to see, with MIT, I said, you're going to break the ties arbitrarily. Here's where we get to see where that just washes out in the code automatically. You don't actually have to add any extra code to say this is how we break ties. The ties just get broken without us having to think about it at all. The way the tie is broken is the order of the nodes in the queue. Lincoln is first in the queue, so Lincoln is going to get to explore MIT. When BBN is dequeued, it's going to look at MIT, see that it's already been explored, and skip it, and then still go to Rand. So the way the tie was broken was the order of Carnegie's neighbors. When we added Carnegie's neighbors, I said it's going to add Case to the queue, it's going to check out Case, and then it's going to check out Harvard. That's going to be determined by the order of those nodes in the adjacency list for Carnegie, which is going to be determined by the order in which the edges were added to the graph. So I'm going to say that this edge was added to the graph before this edge, and that has that cascading effect of making Lincoln explore MIT. So the tie was broken arbitrarily. It was based on the order in which you added the edges. So however you create your graph, like the order in the array list that is the adjacency list, that's going to break the ties for you. So you don't have to actually do anything to break the ties. You just have to make sure that like BBN is not going to explore MIT a second time when there is a tie like that. Which if you code things up the way I'm talking you through it here, it just works. It just works. It's not something you have to think about. So we're going to DQ Lincoln. Lincoln's going to find MIT, mark it as explored, NQ it, and set MIT's distance equal to Lincoln's distance plus 1. Lincoln's distance is 2, so we know, even if we don't think of how to get from Carnegie to Lincoln, we know that its distance is 2. Lincoln's distance is 2. And we just found MIT through one more edge, so 2 plus 1. There must be a way to get from Carnegie to MIT with 3, because we're going to take whatever path it was to get to Lincoln in 2, and then one more we can get to MIT. So MIT is going to get 3. And then Lincoln's going to check out Case. Case has already been explored, so do nothing. Now when we DQ BBN, it's going to look at MIT still, but it sees that it's explored. You're going to check array list dot contains MIT. It contains it. Skip it. Don't do anything. So that's the way the tie is broken, is the first node that gets there, it marks it as explored. The second node sees it's explored and skips it. It's going to look at Harvard, already explored, skip it. Rand has not been explored, so we explore it, NQ it, and set its distance equal to BBN's distance plus 1. So we get 3. And we can start to see a pattern here. The power that this queue has, the work that it's putting in for us, is pretty substantial. What it's doing is exploring all the nodes of distance 1, and then we're going, as we DQ, the order in which we DQ them, we're going to DQ all of the nodes of distance 1, then all of the nodes of distance 2, then all of the nodes of distance 3. We're always going to explore the nodes in non-decreasing order of distance. So when we get to MIT with distance 3 being DQ'd, I can guarantee that I've already visited every single node of distance 2 or less before I get to 3. And when we start NQing nodes from our 3 nodes, from our distance 3 nodes, we're going to NQ all of these nodes of distance 4, and then we're going to DQ all the nodes of distance 4 before we DQ any node of distance 5. We're always getting them in distance order. Which means when I find Utah through MIT, I find this node, MIT has distance 3, and I know I've already DQ'd every node of distance 2, 1, or 0, and when I DQ'd all of those nodes, I never found Utah, then I know Utah does not have distance 3 or less. I know it doesn't have 3 either, because one of the distance 2 nodes would have found it. It would have had to, because we checked the neighbors of every single node of distance 2, and we didn't find Utah. So there is no path from Carnegie to Utah with distance 3, with length 3. So it does not have distance 3. We're guaranteed it doesn't have a distance of 3 or less. And from a node of distance 3, taking one more edge, I can find Utah. And I know Utah doesn't have distance 3 or less, and I have the guarantee that there exists a path of length 4 from Utah. I can take whatever path it was that got me to MIT from Carnegie with 3 edges, and with one more edge I can find Utah. So Utah has to have a distance of 4. So mark it as explored, NQ it, its distance is 4. Check Lincoln, already explored, do nothing. Check BBN, already explored, do nothing. Then Rand, check BBN, already explored, do nothing. But Rand does get 3 more nodes. Mark them all as explored, NQ them all. Mark all their distances as 4. Because Rand's is 3 plus one more edge, that gets us to 4. And then we got all of our distance 4 nodes in the queue. Utah, we're going to explore check MIT, already explored, don't do anything. Check SDC, already explored, do nothing. We find SRC, and this is how we break that 3-way tie, who's fighting over SRC. Well, Utah made it in the queue first because MIT made it in the queue before Rand, because Lincoln made it in the queue before BBN, because Case made it in the queue before Harvard, because Carnegie's adjacency list had Case before Harvard. So they had really cascading effects to get us this path to SRI. So Utah is going to explore SRI, mark it as explored, NQ it, set its distance to 5, Utah's distance plus 1. UCLA, already explored, already explored, already explored. Find Stanford, mark it as explored, NQ it, set its distance to 5 because UCLA's is 4. And then at this point, like visually, we can look at this and say, Our job is done. We have all of the distance numbers. All of our nodes are explored. There's nothing left to do here. But the way we write our code, we're looping until the queue is empty. So we're still going to do the rest of the work. We just know at this point, because we're looking at it, that nothing else is going to happen. But our code would still rip through this. Of course, it's going to do it in milliseconds. So we don't mind. But UCSB, explore all the neighbors, already explored, already explored, already explored. Doesn't do anything. DQ and check its neighbors, already explored, do nothing. SRI, already explored, already explored, already explored, already explored. So it doesn't do anything. DQ Stanford, already explored, doesn't do anything. Now the queue's empty. That's when our code knows to break. It's done. We have an empty queue. There's nothing left to do. That's our code signal that the job's done. And now we're ready for the wrap up of the algorithm. Everything's ran. And we're ready for the last step. We're beyond the big loop that does all of the work, the bulk of the work. And now what we have is a hash map of all the nodes in the graph, or at least all the nodes in the connected component of Carnegie, mapped to their distances from the start node of Carnegie. So we have the distance from Carnegie to any node in the graph. Same thing we had with the levels demonstration, except now we know how to actually code this up, how to do this in the code. So if we're trying to find, say, the distance between Carnegie and Utah, we ran breadth first search with Carnegie as our starting node, and then run the whole thing, get all of the distance from the starting node to any node in the graph, and then go to our graph, grab the value at Utah, say, hey, hash map, what's the value at the key Utah? It returns 4, you return 4, good to go. If the end node is not in this hash map, return -1. That's your whole algorithm. That's the whole thing. That's task 8. Most of it. I have one more thing to say at the end. How to actually build the graph, which is the easier part of the assignment. But once you build the graph, this is what you do. Run breadth first search. Get the distances. Find the distance, return it. Okay, but I got a bonus run of breadth first search for you, is pathfinding. This is something I kind of go back and forth on in my head of should I have you do this or not. But say we don't just want the distance between two nodes, but we actually want to find one of the shortest paths between two nodes. So instead of just returning the shortest path is 5, what if I actually want to know what that path is? What's the sequence of nodes to get from the start to the end? That's what I want. I haven't done this in a while. I haven't had students do it in a while. I have before, though. Maybe I will sometime in the future, but obviously not this summer. If I have pathfinding, then there is a testing utility method, is checking if two paths are both valid. There's a lot more to it. A lot more to task 8 if I add pathfinding. Maybe someday. It is so much more interesting, but it definitely ups the difficulty by a significant amount. Specifically the testing. Testing is a lot harder with pathfinding because you're not just checking did it return the shortest path. You have to check did it return a shortest path. So when there are multiple shortest paths, especially like Carnegie to SRI, when there's a bunch of them, you have to make sure that it's a correct solution, not just the correct solution that your code returns. So you get a lot of test fail to correct solution in Autolab because you're not handling every possible correct solution. So that's the trade-off. That's what it would be. Do I want you getting more practice with multiple correct solutions in your testing? Like maybe. But we do hit it pretty hard, especially on the task 6 where the order doesn't matter. So there's tons of correct solutions and you have to accept any of them. I already do hit you pretty hard on task 6 with that. So I don't know. Anyway, that's my thought process. Right now, I'm on. I don't need you to do pathfinding, but this is what it would be if it were required. So instead of tracking the distance numbers for each node, instead we're going to track which node found that node. So which node were we discovering the neighbors, checking the neighbors of when that node was discovered? and switching up our graph a little bit. So Carnegie, we're going to have some special indicator to say this is the starting node. It might be null or -1 or whatever you want to mark this as the starting node. And then whenever we explore a node, we remember which node we came from when we explored that node. Just to confirm, if we pass all the traces on our midterm, we don't have to take the final. That is correct, with no negative implications on our grade. Also, when can we expect our final grades to be released? I did go through this in... I'll circle back to that. I'm kind of in the middle of something here. But once I get to the end of lecture, I'll circle back to that and explain. The short answer is after the Task 8 final deadline. But I'll explain the timeline of the rest of the semester at the end of lecture here. So we're going to remember, which we're almost at the end, by the way. I'm not going to go through the whole thing tediously like I did with the last run. So each node is going to remember which node explored it. So Harvard was explored by Carnegie. So Carnegie is the one that explored it. Do that for every single node. Rand was found by BBN, etc. for every single node throughout the run of Breadth First Search. And then once we have this information, say we want to find the path from Carnegie to Stanford, a shortest path from Carnegie to Stanford. With this specific one, there's only one shortest path, but whatever shortest path Breadth First Search found after breaking ties, based on the things we already said, we're going to build the path backwards. We're going to start at the end of the path, the end node, and build our way backwards. So we want to get to Stanford. So we know Stanford's the last node in our path, and we're going to ask Stanford, which node found you? It's going to say UCLA, so UCLA is our second to last node. We know that. Then we're just going to repeat the process. UCLA, who found you? Well, Rand. Rand, who found you? BBN. BBN, who found you? Harvard. Harvard, who found you? Carnegie. Carnegie, who found you? Well, I'm the start node. Once we hit the start node, we know we've gotten to the beginning of the path, and we have our shortest path from Carnegie to Stanford that was found by Breadth First Search. So this is the way we can actually do path finding instead of just finding the distance numbers. If we want the distance, we can find the path and then compute the length of this path, and that's our distance as well. So we do get all the information here. But that's the idea of pathfinding. That's how we can do pathfinding, which we did. I actually did have this assignment before. It's a bit much, but it is super fun. I really miss it, but it is a lot also. But at the same time, it's not too much more than what I'm asking you to do here. Yeah, but it is. I don't know. But anyway, here's a game where we have AI characters. So this blue circle is an AI character, and the yellow circle is the player character. And what we want to do is build pathfinding for our AI characters such that they're going to hunt down the player and not get stuck on walls. So if we just do a simple vector math, a subtraction of vectors to find the path that this guy should take, that this AI character is going to go directly into this little wall, get stuck on this corner here, and the game's less fun because the AI is just dumb. You're going to trap them on corners constantly, and they're not going to be much of a challenge. What we want to do instead is use Breadth First Search to find the shortest path that's valid in this game, and have this AI character find this path of nodes in this graph and follow this path to find the player character. So that's what we want to do. So when you're playing the game, this is what you see. You see just the game. You're running around, trying to shoot at enemy characters and and do your thing. But the AI is going to see just the graph that's generated. They're not going to care about how the graphics are rendered or anything. They're going to see this graph. This AI character knows that this is the start node and that this is the end node. Run Breadth First Search starting at this node, and it's going to find the shortest path from this node to any other node in the graph, and it's going to find that shortest path that it'll build backwards. It knows it needs to traverse this path in order to get to the player the fastest without colliding with any walls, and that's the path that it's going to take. It's going to turn this path into vectors and traverse that path to get to where it's supposed to be going. Which I didn't show this in the other lecture at good old jessehartloff.com. And we're always at the first level. Oh, and I'm bad at it. Just bear with me. I have to win. Oh. It's almost the end of the level. This level's just not interesting because there's no pathfinding. But here we can see these AI characters are going, they're taking the shortest path to the base here, but avoiding walls, using the same thing that we just explored. So they're building a graph with all these tiles, with only edges connecting tiles where there are valid moves, and then the AI characters are taking those paths. And with this one specifically, I have diagonals coded, so they are taking the diagonals, which we didn't see in the slides. But they're taking the diagonals and taking the shortest path to the end without getting stuck on any walls. So that was what was once upon a time was an objective, was a task. I assume most people would rather do degrees of separation because it's easier, but the payoff of the other one is so much more interesting. So our task is to compute degrees of separation between actors. So what we want to do with this one is build the graph and then run breadth first search. That's the goal for your task 8. So you're given any number of movies, and I recommend cutting down the cast list for these, especially. Also for task 6 and not quite 7, I guess it's irrelevant, but task 6 also. For your test files, cut down those cast lists just to reduce the amount of work on your brain that you have to think about. So with this, I have 3 movies, and I have to build a graph. I'm going to iterate through these movies, go through the cast list, and for every pair of cast members, I want to add an edge to my graph. So I'm creating my graph of strings, and I'm adding an edge between Jennifer Lawrence and Josh Hutcherson, an edge between Jennifer Lawrence and Elizabeth Banks, and an edge between Josh Hutcherson and Elizabeth Banks. I'm going to add those 3 edges as bidirectional edges to my graph, then move on to the next movie and do the same thing. I'm going to add all these edges for every pair of actors in this movie, and every pair of actors, there's only one pair in this movie, to each other. And then run breadth first search if you have to find the distance between Jennifer Lawrence and Zoe Saldana. We're going to find the path of Zoe Saldana. Again, the actors themselves are the nodes, and there's edges between them if they're in a movie together. So Zoe Saldana, we're going to take the edge to Chris Pratt, take the edge to Elizabeth Banks, and then the edge to Jennifer Lawrence. So Zoe Saldana was in Guardians of the Galaxy with Chris Pratt, who was in the Lego Movie with Elizabeth Banks, who was in Hunger Games with Jennifer Lawrence. So Zoe Saldana, Jennifer Lawrence, their degrees of separation, their distance in this graph in degrees of separation is 3. 1, 2, 3 is 3. I don't know if that's their actual degrees of separation. They might have been in movies together, but if these are the only 3 movies that exist in the world, and these are the only actors in those movies, then their degrees of separation would be 3. So you build the graph based on the movie data, run breadth first search the way we explained for most of today's lecture, and that's your degrees of separation. And that's how to do task 8. So timeline. So just to confirm, if we pass all the traces on the midterm, you don't have to take the final. That is true. There's no negative implications. I'm going to send out emails probably Monday just to absolutely confirm with everybody. I'll send an email to you if you passed. If you have both learning objectives on the midterm, you don't have to take the final exam, but I'll take that a step further and say I'm not even going to send you the final exam. Like, you should not take the final exam. I'm not going to send you an email on Tuesday with the links to the final exam at all. I'll send you an email on Monday just giving you a heads up that says, hey, you just to confirm, you do not have to take the final. You're done. So you can confirm that right now. Go to Autolab if you have both learning objectives for the midterm. then this is it. This is 116. This is the end of it. This is the last lecture that I have. This is lecture 10 out of 10 of 10. 100% of the content is out there now. I don't have anything else to explain to help you with the 8 programming tasks. So if you have both learning objectives on the midterm, there's no final exam for you. And the last thing you have to do is complete all 8 tasks. And if you've completed all 8 tasks already, you're done. That's it. That's 116 for you. And you should enjoy the rest of your summer. Go sip some beverages on a beach somewhere. You're done. So I'll send emails Monday. Maybe I'll send them sooner. I'm busy all weekend, though. I'm not going to bother. But so probably Monday, I'll send out emails just to say, hey, you don't have to take the final. Here's confirmation. And then I'll send the email to anybody who does have to take the final. I'll send the email just like I did for the midterm and say, here's what to expect tomorrow for the final exam. And then for those students who have to take the final exam to pass the class, I'll send the emails on Tuesday, 8 a.m., 11 a.m., depending on your section. I'll send those emails out and do the final exam thing. If you passed OOP but not DS on the midterm, you would only take data structures. We explained this earlier in lecture, but just a reminder. And vice versa. If you pass the data structures, one of the data structures quizzes, so you completed the data structures learning objective on the midterm, but not the OOP learning objective, when you go to the final, when you take the final, only take the OOP quizzes. You got 2 shots at passing that OOP quiz and passing the class, assuming you have all 8 tasks completed. But you should not take the data structures quizzes. Don't even waste your time. Yeah, this is the last lecture. This is it. That's it. I'm done with content. That's 10 of 10. The last lecture is the final exam. And we lose lecture 12 because it's on the 4th of July. So it's a university holiday. We can't have lecture that day. So there would be a 12th one, but I reorganized things, I think, quite well, honestly. So I got everything I need to cover in 10 lectures. So I ain't even mad about losing that 12th one. Yeah, this is it. Everything's in your hands now. Complete the tasks. And then if you need the final exam, not many students need the final exam at all. A pretty small percentage of the course. There's a decent number of students who would need the final exam based on their midterm performance. But as it turns out, probably not too surprisingly to me, a lot of the students who didn't complete both learning objectives on the midterm are also missing final deadlines and failing the class based on their task performance. So there's a correlation there between midterm performance and task performance. Not surprising. Those are probably the students who don't watch lecture or watch lecture at 3 times speed and don't really pay attention to anything that I say. Which is sad. I don't like that. Like it's tough because there's nothing I can do to help those students. Like I can't, like, I don't know what to do at that point. Like, do I force lecture attendance? Like during spring and fall, I do somewhat force lecture attendance, but no matter how much I incentivize it, some students still skip lecture. So, I think those students are just gonna fail no matter what. There's not many students who really try their hardest and fail this course. Anyway, so it's a pretty small number of students who are actually taking the final exam. And it'll go down after test 5 and 6 final deadlines, sadly. What else was I doing? Oh, yeah. And then after the late deadline for task 8, I was doing the timeline. After the late deadline for task 8, at this point, I can finalize all your application objectives. So once this deadline hits, I can process all of the application objectives for the deadlines. Your application objectives for the quizzes, you already have full information of those 8. You know whether you got those or not. The 16 for the deadlines, you do also have all the information for this. You can figure out how you did on all the expected and late deadlines and what application objectives you got out of this 16. But I will give confirmation after this deadline. I'll post on Autolab what your task application objectives are, just so you have confirmation that that I do have record of those application objectives. And at that point, you'll know what your grade is. You'll know for sure what your letter grade is going to be. And I want to do that just in case I have any mistake for any reason on those application objectives. You'll have time to look at those application objectives for a while before final grades are posted. So in the hopefully unlikely chance that I make a mistake there, you can send me an email, be like, hey, or a Piazza post, hey, my AOs are off for my tasks. I did meet this deadline. Give me my application objectives. One situation where that has happened in the past, but I look for it now. I have scripts and stuff that check for this now. But if a student submits before the expected deadline, gets credit, earns their 2 AOs, and then after the deadline they submit again, usually accidentally, but they submit again, get credit again, but after the deadline. Sometimes that, I miss that. I know to look for that these days. I shouldn't make that mistake. But any mistake like that where some weird situation happens, sometimes, your application objective might be missed. So just giving you the chance to double check that. I'll start processing them here. So probably during the final exam where I'm just sitting there watching Piazza, hoping that things don't fall apart again like they did for the midterm. I'll be processing application objectives and post them sometime on Tuesday. And then it's not until the Task 8 final deadline that I can actually post final grades. I won't know final grades until after this deadline. So unless in the rare situation where everyone who's still in the running to pass the class does complete Task 8 before this final deadline, in that situation I might be able to post final grades a little bit sooner. But most likely there will be a handful of students who are stressing right up until this deadline to know whether or not they're going to pass the class. So I can't post final grades until July 9th, since this is right at the end of July 8th. So July 9th, I'll be posting final grades. Possibly right at midnight, because I'll have most of the information. I'll just be waiting for a few students at that point. So possibly right at midnight on July 9th. So that's the timeline and everything. We do technically have another half hour in lecture. So at this point, as I alluded to at the beginning of the lecture, I'll take requests if anybody has them. Anything else you want to see? And if not, I'm just going to shut her down. In the other lecture, we did go through this memory diagram. I don't think it's super useful. I don't think it was in the earlier lecture. It might be. If you want to see it, I'm happy to go through it. But I don't want to go through it if nobody cares. Because I don't, you're not going to do a graph memory diagram. I'm not going to throw a graph memory diagram at you on the final exam. Can you do the trace data structures, please? Sure. We have a request. Let's do it. I am going to do it on slides, though. I'm not doing it on the tracing tool. I don't even think we have enough time to do it in the tracing tool, to be honest. But I will do it in the... Wait, can you trace data structures, please? I don't understand the logic flow. I'm really struggling. Oh, you're not even asking for this memory diagram. There are multiple data structures quizzes. Ooh, I don't know if I will take this request. Depends which one you mean. I can walk you through the sample data structures quiz. That would be... Oh, son of a bitch. What's the easiest way to get there? Let me do it this way. Because if you mean the sample data structures quiz, I can walk you through the image that I posted. It'd probably be the best way to practice. But this is something that works better with specific questions. So this might be more of an office hour question. But I'll do what I can here. Practice quiz solutions, practice DS. Okay. come on. Can you please trace DS1 or 2? I'm not going to do the midterm traces in lecture. Midterm traces, if you come to office hours with your trace for the midterm, I can go over it. I'll go over what you specifically did wrong, but I'm not going to flat out just go through the midterm solutions for that one. But I'll go through the trace solutions since I posted them. But is this even being asked for? I don't want to do something that nobody wants to see. And I feel like I just said this in this lecture, right? To practice for the final, doing your 2 midterm traces and the sample trace. Those are the ones to study. If you study all 3 of those and you got a good grasp on everything that's going on, that's the best way to study for this. And by the way, right now, even if you have specific questions on the midterm traces, I could do that too. I'm just not going through like live tracing the entire exam, any of the exam quizzes. Or something else I was just gonna say. What was it? I'd like this trace done. Okay, yeah, I can walk through this one. Let's see what the easiest way to do this is. It's really annoying that it does that. It is already maximum. I can't zoom in when it's in full screen mode. It's bullshit. And this was the best way to get one image with the entire trace on it. Is it easier just to go through this whole thing live? No, that's not the easiest way. Maybe it is. No, I don't think so. So the constructor calls, I don't think anybody messed up the constructor calls actually on the quiz. So I can go through these ones pretty quick. We have constructor calls, value, left, right, and just making sure we get left and right correct here. So each constructor is going to return to a variable on the stack. So making sure we have our return arrows, which return arrows are not strictly required. They should be there, but I'm not going to fail anybody if they're missing even every single return arrows. But I did have cases where I was grading quizzes where they didn't have return arrows and they had other mistakes where it would have been clear. For example, traverse returns to left answer right here, where answer and left answer were not the same value and they didn't have their return arrow. Well, now I don't know if you understand even where values return to. So return arrows can only help you. They're never going to hurt your grade by missing them, but having them might be enough information for me to know that you actually do know what you're talking about and made a simple, like you hit the wrong number key and just have the wrong number. That's way different than not understanding how methods return when it's in recursion. Because I know you know how methods return, but when it's in recursion specifically, it gets, it's another layer that's a 116 topic, and I need to know that you understand how that one works. So return arrows pointing to all our variables on the main stack frame, making sure that we have our left and right correct. So it's left, then right. I did see somebody on the midterm where left and right were reversed, and their whole tree was backwards. I believe in that case they did still end up getting credit, like just based on the tree that they built, they still traversed it correctly. So I'm like, yeah, that's fine. But making sure we have our left and right values. And then traversal, this is where things really get deep. So traverse takes the root node. So this one, it's a static method, so there's no this in the stack frames for traverse. It's just node, and node starts at root. So our first traverse stack frame is the traverse frame where node is 0x005, which is the value of root. So we start off with 0x005, and then the first thing we do in this method, this is going to be a pain going back and forth. The first thing we do in this method is set answer equal to 0. So we're declaring a variable when we're assigning it the value 0. And then we're going to check node.getLeft not equal null. This is a method call every single time, and I'm baffled at the amount of you who didn't do this. Most of you passed anyway, but it's still like, why are you all making this mistake? Whenever you see a method call, there's a stack frame. There's a stack frame for every single method call. Node.getLeft is a method call. It's a method being called through the node object, which is a binary tree node. So we're calling getLeft, where this is equal to the calling object, that calling node. So the first two things that a traverse stack frame does is add answer with the value 0, and then makes a call to getLeft where this is the node for that traversal, 0x05 in this case. So we're calling getLeft, that answer that returns, and that's being used in this check and checking if it's not null. So for the root node, left is not null. It's 0x04, so it's not null, which means we're going into this conditional. Can we still draw a return arrow in the tracing tool when the recursive call returns to a return statement in the previous recursive call rather than returning to a variable? If you still have your arrow, I'm not going to get mad at you if you're just adding it there. For the quizzes, I like to return to a variable just to avoid this specific question. So since traverse returns to a variable, and I did the same thing on the midterm, I'll do the same thing on the final, the recursive calls are going to return to variables. So it's more clear in your memory diagram if you did do the right thing, because you should have a return arrow and that value should be in a variable. I can see during the traversal of the tree, did you have the right intermediate values? Specifically when you have a mistake, like when you don't return the right final answer, I want to be able to see where you made a mistake. Because sometimes it's a simple math error, like a traversal like this, where you're taking the sum of all the values in the tree. Maybe you get 11 instead of 10 when you add up these values. Like, I want to know where the mistake was. If it was a simple math error, and I have you returning recursive call answers into variables, it's easy for me to find out if it was a math error and then still give you credit. But if I have it just return traverse, then it's hard, or answer plus equals traverse. It's a bit harder for me to tell if it was a math error or if you actually made a mistake. So I like to do this on the quizzes, return to values. So if we have this is true, so we do get into the stack frame here, and here we have another call to get left. So that's another frame on the stack to resolve the argument for the traverse method. So we have a get left stack frame and a traverse stack frame, and the traverse stack frame returns to left answer in this stack frame. And this is inside a code block. So quite a few moving parts with this one. We have a code block with left answer that's going to have a call of traverse that returns to it, where the node is whatever get left returned, and get left, it is another stack frame. So we have two get lefts here, both with 0x05, because it shows up in the code twice. Like, if it shows up in the code twice, you're calling it twice. Well, not in every case, but you hit that method call twice when you're tracing through the code. So there's two stack frames for it. And then traverse with node of 0x04, we're going to start at the top of the method and start the whole thing over again. And these return arrows really help, because by the time you're done with this stack frame, by the time this stack frame does all of its stuff, you're probably going to forget where you were up here. But now you don't have to think about it. You follow the return arrow. Oh yeah, that value goes right here. We just got left answer. Well, if we just got left answer, well, we must be right here. And then you continue the execution of the other stack frame whenever you get there. But it's going to be a while before we get back there. So the return arrows really help you keep track of what's going on with this recursion. And get left. Get left. If this is true, we hit another get left. There's 2 get left calls here. Now with the midterm, I got sick of doing 2 get lefts and 2 get rights. It was a little more tedious. So I had get left return to a variable called left, and then I used left and left here instead of get left both times. And many of you did not put your left and right variables on the stack frame. There should be a call to get left that returns to the variable left. There should be a call to get right that returns to the variable right. And so many of you did not have those. You had the calls to get left and get right, but you didn't put the variable in the stack frame, which I don't even know what to make of that. If that was overstudying the sample midterms, I think it was a mistake to give you sample traces, to be honest, and going through these and giving you a midterm that's so similar to the sample trace. I think a lot of you might have got away with one there of overstudying and not tracing through the code that you're given, unfortunately. I ain't going to worry about it too much, but I'm going to avoid that mistake in the future. So this traversal returns the left answer, so we start again at traversal. Answer equals 0, get left. And with this one, we're at OX004. Get left returns null, so we do not go into that conditional. We call get value and add that to answer. Then call get right, check if it's null. It's not going to be, so we're going to have another get right. So in this next traversal with OX004, we initialize answer to 0. We call get left, that returns null, so we do not go into the code block for the left call. We call get value, that returns the value of this node, which is 3. And we add that to answer. So we cross out 0 and add 3. If you had a return arrow for get value and had it return to answer, I wouldn't be mad at that at all. But it technically doesn't return to, it's not assigned to the variable, it's added to the variable. It's nuanced. If you have the arrow or don't have the arrow, I call both equally correct for this case. So then that's 3. And then we call get right. Get right is going to return something that's not null. And then we call get right again to set up the next traversal call with that node, with the right node, which is OX003. The next call to traversal goes back to the top of the code, sets answer to 0, calls get left. 3 is a leaf node. It doesn't have any child nodes, so get left returns null. We do not go into the left code block. Get value, add the value of this node, which is 2, to answer. Call get right, which also returns null, so we do not go into the right code block either, and we don't call get right a second time. And then we return answer, which is 2, over to wherever the return arrow goes. I already forgot what we were doing in the whole stack frame, but never fear, I have a return arrow. I'm just going to follow that arrow. Okay, I'm returning 2, goes right here to right answer in this stack frame. If I'm assigning to right answer, I know that I'm right here. I must be on this line because we only assigned to right answer one time. And then we're going to add right answer to answer and then return answer. So in that stack frame, we're going to add right answer to answer, cross out the 3, it's up to 5 now, cross out the code block for right answer, and then cross out the stack frame and return the answer of 5 back to whoever called this. So we return 5. I'm just going to follow the return arrow because I forgot where I was in the recursion. There's way too much for my brain to keep track of. I'm just going to follow the return arrow. Okay, it goes right here. We return 5. That was left answer. So in this stack frame, we must be at the line where we're assigning to left answer. We must be right here. So I'm going to pick up execution right here. Answer plus equals left answer. Then add this node's value. Then do the same thing over to the right. So answer plus equals left answer. So answer plus equals left answer. That 0 goes to a 5. We reach the end of this code block. So this code block is gone. Left answer is no longer in memory. We call get value. And this is where, if you're just looking at the solution, things start getting really tricky to follow. If you're doing the trace live, if you're working through this for practice, it's easier to see. Looking at just the solution, it's a little harder to see this. But we're going to call get value on this stack frame right here. At that point in time, all of this stuff happened. All of this already happened. We just walked through all of these stack frames. They're all crossed out. So that get value with OX005 is way down here. It's nowhere close to the traverse stack frame that we're actually working with. And then this returns the value at that node and adds it to up here, adds it to answer. So we add 4 to 5, we get to 9. And then we're going to call get right, which is not null. So we call get right again, and then call traverse on the right node, which is OX02. So we have our traverse call for OX02. Its left and right are both null, so we don't go into those code blocks. Its value is 1. So we're going to add 1 to answer and then return that all the way back up to right answer in our first stack frame at the root node. Gets 1, add 1 to our answer, cross out the code block, cross out the stack frame returning answer, which is 10, and that goes to our return arrow here. Again, very helpful to have your return arrows right away because I'm just going to follow my return arrows once a stack frame is done with its job. Returns way up here, result is 10, and then print 10 to the screen. So my advice when going through a trace like this is to shut off your brain a little bit. Don't overthink. I see way too many students doing poorly on quizzes because they overthink it. Because here's an approach what a lot of, dare I say, unsuccessful students do. Is that the best way to say it? Is they'll look at this code, they'll draw out the tree, because any one of you can look at this code and figure out what the tree is going to be. And then any one of you can also look at this code and figure out what we're doing. You might say this is an in-order traversal that's summing up all of the values in the tree. With a little bit of work, I mean, that's tougher than looking at the structure of the tree, but with a little bit of looking at this code, you'll figure out that that's what it's doing, that's its intent. And then you'll add up these values and you know that the answer is 10. So the first thing you do is write result 10. You go over to your stack frame, you do result 10. You print 10 to the screen. And then try to kind of BS your traverse calls and just try to write any crap down here that you think is what would actually happen, and just pray that I see that you got the right answer and give you credit based on that. That's what some students do. I might not be describing anybody who's watching this lecture, but that's what some students do. And that's such a horrible approach. Hopefully I don't have to really explain why that's so bad, but I'm gonna explain a better approach. The better approach is to do what the computer does. The computer doesn't think at all, much less overthink things, because that's way overthinking things. You shouldn't analyze the code to figure out what it's supposed to be doing or what you expect it to be doing. You can, as a double check, like after you're done with your trace, then go back and say, okay, what is this code supposed to be doing? And do that as a sanity check, that's fine. But don't do that to generate your trace, because you're going to end up skipping a lot of steps, and you're going to end up filling in a bunch of steps that you force to do what you think the code's supposed to do. This is very detrimental if you're wrong about what the code does. So if you have a wrong assumption, if you're like, I think this multiplies all the values together, and you try to force your trace to be that, you're definitely going to, you're not going to do well. What I suggest to do is do what the computer does. Take it one line at a time. One line at a time, and just blindly read through the code. I have a constructor call for binary tree node with one null null. So 1 value is 1, left is null, right is null. This dot value is value. Go over to the heap, set that instance variable value to value, which is 1. Set right equal to right, left equal to left. And that ends, so this returns a reference to node 1. Do the same thing for the other constructors. With traverse, I have a traverse call. Root, okay, node is root, which is whatever reference this object got. Answer equals 1. I'm going to create a variable named answer in the stack frame, or is equal to 0, and set it equal to 0. Node.getLeft. If I see parentheses, I'm thinking, holy shit, there is a stack frame that has to go on the stack because I just saw 2 parentheses. This is a stack frame on the stack. Every time you hit parentheses, there's a stack frame on the stack. Okay, so now node is the calling object. This is a non-static method call, so this is going to be whatever reference is in node. I got a getLeft call. Whatever that returns, I'm checking if it's null. If it's not null, I have a code block. I have a variable declared in that code block, so I'm going to actually need my dashed box. Put left answer on that code block. Holy shit, I have parentheses. I got 2 sets of parentheses. I better see 2 stack frames. The argument has to be resolved first, so I'm going to put this getLeft stack frame on the stack. Whatever that resolves to is going to be the parameter with the parameter of traverse gets. Put my traverse on the stack frame. That parameter is node, which gets the value of whatever getLeft just returned. And traverse return, set up my return arrow to left answer inside that code block. Then go through traverse again. Go back to the top with the next node. Answer equals 0. Go through the same stuff and just line by line it. Don't overthink it. Don't get ahead of yourself. Don't think, oh, this is what the code is about to do. This is what it's supposed to do. Just line by line it. Turn your brain off a little bit. Take it easy. Take deep breaths. One line at a time. One statement or one expression at a time even. And just take it nice and slow. And don't skip any steps. That's my recommendation for this. How do you know it's a code block? You got braces. If there's an open brace and a closed brace, you got yourself a code block. And since there's a variable that's declared in it, so not all code blocks need code blocks in your memory diagram, but once there's a variable declared inside of it, then we're going to need a dashed box in our memory diagram. If there's no variable declared in it, you could still create your code block, but it's going to be empty, so there's just no reason to add it. You can just have an empty code block. That's fine. I'll never get mad at you for having an empty code block, but I don't require it. I'm not gonna ask you to do that. So we have braces. I'm thinking code block. If I have parentheses, I'm thinking stack frame. I see an equal sign. I know I'm either declaring a new variable. If there's a type, then I'm declaring a new variable. There's a new variable on the stack. If I see an equal sign and there's no type here, I'm not declaring a variable. I'm reassigning a variable. So whenever I see an equal sign without a type before the variable name, I know I'm crossing out a value and putting in a new value. So when you trace through the code, every time you hit one of those cases, you know what you're going to do. You see parentheses, stack frame. You see braces, code block. You see equal sign with a type for the variable name, new variable in that stack. You see an equal sign with no type, there's no new variable, but you're going to cross out a value of a variable and write in a new variable. Just blindly go through and do whatever each line of code is telling you to do. Way too much overthinking on stack frame. Either overthinking or just being, what I fear is that it's just complete cluelessness and over studying the samples and the lecture examples. Because I see way too many bad solutions, bad submissions that look almost identical to either the sample or something I've done in lecture. Like not having left and right was the example I just gave. I just did things slightly different between the sample and this one, and like a lot of you missed that one and didn't do it right. And I think that's just overstudying, especially when you're allowed to have the sample right in front of your face during the midterm. I think a lot of you were just copying that over to this and trying to catch the differences. which isn't the way I recommend to do it. Please don't do it like that. Don't do that. Go through one line at a time. Deep breaths. Try to relax one line at a time, and just do what each line is telling you to do. Okay, and we actually did fill up the whole time with that. That was good for anyone who has to take the final. That should be good preparation if you have to take the DS final, especially. But even the OP final, take it one line at a time. Don't forget your superclass constructor calls. But if you're taking it one line at a time, on the midterm and the final and the sample, but the final is the only unknown out of those three. I'm going to explicitly have the superclass constructor calls. So if you're taking it one line at a time, you're going to get to the line that says super. So it's impossible to forget. You cannot possibly forget your superclass constructor calls if you're just tracing one line at a time. But if you're thinking ahead, if you're skipping around, if you're making assumptions and just trying to make your trace, force it to look like the sample trace from the sample quiz, those are the things that get y'all in trouble. Just take it one line at a time and actually read the code. And if you can't read the code, if you're going one line at a time and you can't read the code, there's a fundamental issue there that needs to be resolved. Come to office hours and I can help you understand what code is doing. Because reading code is an extremely critical skill in this field. You have to be able to read code and write code. Those are the two big things we got to do. And often you do more reading code than writing code, to be honest. So if you can't tell what code does by reading it, and exactly how it does it, getting back to one of the themes of 116, a good wrap-up phrase, how the code works. If you don't understand how the code works and you just know that this is going to take the sum of the tree, but you don't really know how it does that, and you can't trace through everything that happens in memory, then you don't really know how that code works. So that's something that we need you to be able to do by the time you get out of 116. And yeah, we did fill up the time. Cool. And that's it. That's the last lecture. I'm out. Those of you who don't have to take the final, wrap up your eight programming tests, then you out. If you passed OP and DS on the midterm and you have all 8 programming tests done, then that's 116 for you. You're done. You're out of here. You're already all wrapped up. But if you need to take the final, I'll see you then. I'll send emails and we'll do the final the same structure as the midterm. If you have to wrap up the tasks, we have office hours. I'll be in office hours in half an hour. We have Piazza still. Get the help, any help you need on those. Make sure you're hitting those final deadlines at the very least in passing the class. But hopefully you're hitting expected deadlines and at least late deadlines. But make sure you're not hitting the scary red ones. Relying on those is very dangerous, as many students have found out. Somebody started task 4 on June 24th and couldn't finish it and sent me emails about it. Like, you gave yourself one day. I mean, anyway, but yeah, once you're finished with the tests and the midterm or the final, if you have to take it, that's it. That's 116. I'm done lecturing. This is the last time I'm going live on YouTube for the summer. So that's it for me. Unless you see me in office hours, you're not going to hear from me again. Or you're taking the final exam. So good luck, everybody. If you are done with the course, enjoy the rest of your summer. If you are wrapping up, get done with things and then have a great rest of your summer.